All right, so we're going to look at this limit question here. And so notice that it tells us already what the limit is. So what we're being asked to do is justify that. And they've told us to use this special limit, which is one we looked at previously in a video. And so this is one you actually should know. We proved this using triangle and a circle and sandwich theorem. And we proved that this limit is 1. And so we call that our special limit. So here we're going to use that special limit to derive another limit here and justify why this limit is 0. All right, so the first thing that we might notice is that the problem we started with here involves cosine, and the special limit that we have over here involves sine. So we need some way to convert from cosines to sines. So we're going to need a trig identity, and this may or may not be one of the ones that you remember. But once I write down that trig identity, you should be able to see how we can use that to convert the expression we have to look more like this special limit form that we have here. All right, so in trigonometry, you would have probably called this a double angle identity. It's a double angle identity for cosine of 2 theta. And there's several different ones for that identity, but the one that relates cosine to sine is 1 minus 2 sine squared theta. All right, so that's the identity that we're going to use. We might notice that in that identity we have a cosine 2 theta, and here we have a cosine of x. So we need to think about how we could rewrite that cosine of x as cosine of 2 times something. All right, so I might notice that I could write that cosine of x as cosine of 2 times 1/2 x, or 2 times x over 2. So that x over 2 would be our theta, so that this is cosine 2 theta. All right, so when I use that identity on the problem that we're working on over here, we're going to convert that to sine. So in the numerator here, I will have the original expression that we have there. I'm just going to rewrite that down. The limit as x approaches 0 of cosine of x minus 1 all over x. I'm going to use this identity on the cosine of x. Right, so I'm going to rewrite that. All right, so instead of cosine of x, I'm thinking of that as cosine of 2 times x over 2. So this theta will be our x over 2. And so I'm going to replace all this in place of that cosine x. 1 minus 2 sine squared of x over 2. And then I have this minus 1 that was part of the original expression here on the numerator, all over x. All right, so we're getting a little bit closer to the form that we have here. You might notice that I have a couple of 1s that conveniently cancel there. All right, so I might notice, though, that I have sine squared of x over 2 instead of just sine theta over theta. But we did some videos like this before with slightly less complicated expressions than this, where we basically just did some rearranging and regrouping this expression so that we get a group that is of this form. And then hopefully we can look at those other forms and look at what's going on with those other limits. So I'm just going to do a little bit of regrouping here. All right, so I'm going to pull this minus 2 kind of out front. So we'll have minus 2 times. And then this sine squared of x over 2, I'm going to pull that apart into one of the sines of x over 2. And I'm going to put that over this x that's on the denominator. And then I'll have the other sine of x over 2 that's left over from that sine squared as a separate factor. So I've just done a little bit of pulling this apart. We did this with some other problems that we looked at in previous videos. But the goal was to force this special limit form. So we're getting a little bit closer here to this sine theta over theta form right here. All right, so we might notice that instead of theta, I have x over 2 here. And so I wish this denominator were also x over 2. So we did some problems like that before, too. We talked about that as long as you're using legal algebra, you can manipulate that. And so I can multiply this denominator by 1/2. So that denominator is now x over 2, so that these match. This both would be our theta. As long as I also balance that. So wherever in this expression, I just need to multiply on the numerator. Here I divided by 1/2. I need to multiply by 1/2 to balance that, wherever I want to do that. I'm going to go ahead and put that in this grouping here where I have the other constant. So those 1/2 that I put there algebraically balance each other. I'm multiplying and dividing by 1/2. The reason I put the 1 here in the second grouping was so that I could get the sine theta over theta form. All right, and then at that point, we have all expressions where we can evaluate the limit. And so now all we need to do is use our limit laws to think a little bit about what each of these limits is. All right, so as x approaches 0, this first part here is just constant. As x approaches whatever it's approaching, I have -2 times 1/2, so that part is just -1. This is our sine theta over theta form, and as x approaches 0, 1/2 x is also approaching 0. So that is this special form that they asked us to use. So that was from a special limit. And then this last expression here, this sine x over 2, that function is well behaved. We have some substitution shortcut theorems that talk about for trigonometric functions. As long as we're in the domain of the trigonometric function, we can do a substitution shortcut here. So here we can just do that, and we get sine of 0. And sine of 0 is 0. So I'm just going to replace that parentheses with 0. So I have -1 times 0, and I just get 0. All right, so we used this special limit that we had derived using a sandwich theorem, a triangle, and a circle to prove that this limit is 1. And now we've used that to derive another special limit. Both of these two special limits will come up in some other applications later in the course. We will need to leverage those later for some other things. So we started with this one, we used that to generate this other one, and these will definitely come up again. These are both things that perhaps are worth memorizing, so you don't have to go through this derivation every time. So work on memorizing those.